All right, so here's a video or series of videos I'm calling week 7.5 because I hadn't done any topics on phase stuff. So we're taking trying to recover some information on phases. So here's some stuff I've taken from Beard Johnston. Uh, some equations. Let's start with an equation like here, right? So this is for the undamped free vibration, right? Our basic spring and a mass. And here's our general solution. I already put a little check mark next to it. Before we do anything with initial conditions to try to find, we have these two constants right here. Now, if we would rather have a more compact form and have a single magnitude and get rid of the cosine by including this phase right here, I don't have the identity written down, but it's a trigonomic identity, which allows us to combine these two things together. And what we have is a magnitude, which is just the sum of the squares. And then we also have a phase, which is going to be the inverse tangent of C2 over C1. Some books, I see that they have a negative sign in there. I think that usually happens when they flip these two things around. All right, so just be aware. Also note that some books like to use this symbol, let's call it psi, for our phase, and some use phi or phi. Never sure which way to pronounce that. Down here is an interesting figure that helps us, I think, get sort of a picture of how phase works, right? So you have a dot right here representing this on a time history. And you kind of see that here is the coefficient right here for this guy. And right here is the coefficient for this. So what we're really getting at, and let me switch colors to, is this vector is what we're describing. And okay, so we rotated in this amount of angle right here, right? So at this position in time, right here, we have omega n, the natural frequency time, t, times this t, and that's brought us to that position with respect to time, which is described by this right here. But you can also see that there's a phase angle right in there. So that's a good image. We're going to come up with some other images that can kind of help cement the role of phase in the basic vibration things. Here's another one. We've already covered this one. This out of our textbook, out of Thompson. Where we see here's our position. And we kind of already know that to expect that when we get to this maximum right here, that we're going to get a minimum right there. Not a minimum, we're going to get a 0. And we're going to get a minimum right there, right? So it's kind of easy to see that the velocity here is 90 degrees ahead in terms of phase of the position. Same thing true here with our acceleration. It is 90 degrees ahead, right? So it all depends on where you want to start counting this from. I suppose we could say, yeah, I think that's fair right there. All right, so we could just say acceleration is ahead by 180 degrees, while velocity is ahead by 90 degrees from the position. Yeah, okay, because this is 90 degrees and this is 180 degrees. and this is 270, and that's 360 degrees for measuring there. All right, so we should also recall that we could get these initial conditions from, use the initial conditions to replace those coefficients, the ones that we had over here, these guys. They can be replaced by these. And so getting it back into this form, we can, it could follow that we have this equation. Now, we don't write that out all that often. We might write out what the values are separately as this, and then put them in here. Here's another version of the same equation by Inman, where you can see how they've assembled things. And then in here, they don't use the x dot 0. They use the just a v0 to represent the initial velocity. Another example here of another way to write out this amplitude right here from the initial conditions. You can kind of see that this is going to be the same thing. All they've done is they've removed the natural frequency to the outside. And they've also gotten the phase angle. So here's another view of the shift of this phase angle right here. And of course, remember, this is the time right here. So they divided the angle in radians by the natural frequency. And of course, that's going to turn out to be time, right? Because you're going to have radians divided by radians per second. That'll come out as time. So here is a perspective on what that phase angle really means and where it's starting. All right, so here's the underdamped free vibration, right? So we're moving on. We just had the free vibration phase considerations. Here's for the underdamped. All right, now recognize that the overdamped and critically damped, they don't have any phase issues because they're not really vibration, right? Because they're more like that kind of thing, or even that kind of thing. These are what the overdamped and the critically damped look like, and so they don't have any phase. This thing never actually touches. All right, so we're going back to this setup right here. All right, so this is the main guy that's oscillating. This is just decreasing the oscillation with time. So once you put into the initial conditions, we've already done that. So if with the initial conditions, initial position, initial velocity, you can see that we have these two pieces right here. Oh, I just replaced some things. So I just replaced, okay. So this guy right here, I could replace with these. Anybody else? No, that's all. No, I also did these. Okay, so we replaced those little pieces right there. And so this is the form that we would like to get the above into. So we could calculate separately a magnitude based on, let's go a little bit of highlighter in here. Based on that piece and that piece right here, right? So under that amplitude, but also shifted by this inverse tangent of those two pieces. And hopefully that shows through right in there. Looking. Oh yeah, okay, so here's the XO from up there, right? Yeah, so there's that XO. It ended up down here. Yeah, so that works out. And once again, it's like, oh wait, let me think about this for a second. And I'm making sure that I wrote this one correctly. I'm a little concerned I didn't write this correctly. Because we have this XO, and that should be here. And we have this. So I'm kind of thinking maybe this one should have another XO in it. So be cautious when trying to use the notes for anything right here. We want to double check that we don't have another XO that's supposed to be right in there. So undamped forced vibration, we've already noted that we have, this is the equation of motion for this, and then it's a non-homogeneous solution, and it's really the particular part that we care about. Here is an interesting thing, right? So to this side, we have a phase that's in it, so that we'll write that this is in phase. And to this side, we are 180 degrees, and we'll say that's out of phase. Of course, it kind of 180 degrees almost kind of already it assumes that you know that you mean you're going to be out of phase. So let's actually see this from I don't know where the E came from the Miriam and Craig. It says for to the left any omegas that are less than the natural frequency, this is a positive value. This magnitude right here is positive. And you even see it in this one right here. They, not like in others, they put an absolute value on top of that. You might recall from, I guess it was the Beard-Johnson book, we saw like something like that right there, actually onto the right-hand side because it was negative. But I digressed. The vibration is in phase with the force, right? So that means like as your force is going up, your magnet, the resulting xm because of this force. Well, let's go pm because that's how I wrote it up here. The pm is coming up this way. That's over on that side. But in the other case, when we have an omega that is greater than the natural frequency, the magnification factor ends up being negative, and the vibration is 100 degrees, 80 degrees out of phase, right? So if we have a force, let's make the force going upward. As the force is going upward, PM, the reaction moment, I want to say the response moment, translation, I said moment, but I meant translation. The response translation is going the opposite, so it's out of phase. And now we get to the underdamped forced vibration, right? So we got the whole kit and caboodle, and we have this as our equation of motion. And but note that I switched these magnitudes just to match the figure because they had this in the figure. Here is a really important figure to kind of consider here, right? So you have several forces acting on here. You have four forces, if you want to think of it in those terms. You have the mass times acceleration, the damping times velocity, and you have the stiffness times position, and now you have the magnitude of the force, right? So if, oops, excuse me. I don't know how that happened. Can I get out of that? Why are you like that? There you go. That clicked it. I guess. All right. So anyway, here is this, and here is at a given time. Right. So we're doing like a little time history of what's taking place. Right. So if this is the force right here, we have a little bit more of a complex thing going on in terms of response. But we could see that right there. This is actually going to be that X, if you will, when we get done and we get some type of this guy right here, right? So that's going to be the X. They're going to be out of phase with each other, right? And I'm probably not doing it correctly, but it should be the same frequency as my as the forcing frequency, but they're not going to be in phase with each other. And so how much in phase are they going to be? Well, you kind of walk through, and like here is the result, if you will. But so you could say that this is sort of like going to be well, they're actually saying that this is the phase angle. So excuse me from there. So they're measuring how much out of phase they're going to be, right? So this, I'm trying to get this correct. I don't know if I will, but I don't. I just drew this randomly, so I'm not sure I'm going to. But let's say this guy right there and that guy right there, right? So I can't say for sure, and because this is a time history, right? These are both times of this thing happening. That should be like phase divided by, let's call it forcing frequency, right? So here is the phase that's in between the position and the force. You can also see how this gets constructed. Is this going to be a vector thing between these forces, because we have to have, here's going to be your spring force, here is your dampening force, and then here's your acceleration force. And you'll notice that once again, these are 90 degrees from each other, and then these are 90 degrees. Therefore, this one and this one are 180 degrees out of each other, and then they complete the vector. And it needs to do that because this is an equation right here. That equation still holds true. And recall that this right here is the equivalent of x dot, and this right here is the equivalent of x double dot. After, if you're just going with magnitudes. So here are the equations that we end up with, or at least the first set of equations that we can end up with for our response, right? And if you do a little bit of massaging, this is one I like a lot better. Probably one that I would go to more often, because this is like the magnification factor. And then, but here is the phase. And if you work through it a little bit, you would see that that's true. Notice that we could find some stuff about the phase with this ratio right here, right? That right there is just a graph of this phase angle. Let's see, what else do I want to say? This is also in our book. So here's our transmissibility magnification factor. And here is our phase thing. You could notice that our phase is 90 degrees. So we were 90 degrees response when we are at resonance. Okay, so that means that when our force is completely to its peak, it's at its peak, we should be okay, because we only have like a single degree of freedom, remember, and we have like let's say we have this guy right here, and so we have our well, okay, so so he's at his maximum right here. We are at the we're kind of like passing through the equilibrium, right? Because this is pretty much going to be for the x. This is going to be the zero position right here at equilibrium, right? So the force is going to be at a maximum while this thing is at a zero. And so that's what this piece means. But you can also, so here's the figure out of the book where that shows right there that we are at 90 degrees to each other when we were at resonance. And then the same kind of idea that presents itself when we were the undamped, where we said, okay, to the left is going to be in phase, to the right it's going to be out of phase. Right, so this is neither in phase or out of phase here because they're 90 degrees from each other. So right here we're going to be this direction over there, and I want to say that the force is leading the response, and on this the force is sort of lagging the response. That's what at least I want to say. Anything out of this Miriam and Craig that I want to discuss? We do have this phase angle equation at the bottom to keep us a reference, and then it's related to these. The phase angle can vary from 0 to pi, right? So it goes from to 0 degrees to 180 degrees, and represents the part of a cycle, and thus the time by which the response lags the forcing function f. I said lead when I meant lag before, right? So, oh, wait a minute. I think I said it right. It said response lags the forcing function. Okay, yeah, I got it right. So this is lagging behind that as it's rotating around. Like let's assume that this thing is kind of moving around in time. It could be just thought of as being like stationary as we look at a snapshot. I think of it as rotating. Probably because I go back to this image, maybe that image, more like this image right here, right? That and I'm probably thinking of more of this as a clockwise motion right there for some reason. Anyway, that's the lead and the lag kind of concept, and shows how the phase angle varies with the frequency ratio, and the damping ratio, right? So you could see that right here it's an either or type of thing when the damping is 0. That's the undamped response. And note that when it's okay, there's 90 for all values. To further illustrate the phase differences between the response and the forcing function, we don't, because I didn't bother showing that figure. Oh, no, there is. Okay, there you go. This figure right here. This is really one of the reasons why I wanted to show this and include it in the supplemental notes. We show we have two examples of the variation of F and X, the response with omega t, right? And remember that they're not putting F's on omega, so that's what I mean is omega F. In the first example, omega is less than here, so this is going to be to the left-hand side. And so that right here we're going to take it as, pi over 4, all right? So we're like 45 degrees. So let's take a look at that right there. So you can see that if we plot both of them on here is going to be the xp, and here is going to be the forcing function right onto there. And this is, okay, so this one is rotating counterclockwise. So it looks different than that figure from Beer-Johnson, unfortunately. But you can get kind of the idea of how it's lagging behind. But in here, right, so now we have where we have on the right-hand side, omega call it omega F, is greater than omega N, so we have an R that's greater than 1. And you could see that now, let's see how the words said right here. In the second example, this phi is taken to be 3 pi over 4 for that lag, which is still that's what, 135 degrees. Yeah, okay, sure, 135 degrees, and you can see that they've now that the angle has taken over here, right? So still F is still leading as far as I can tell in front of that. So that's kind of interesting. I wanted to say that it was going to be lagging, but you still see that that X response is ahead of the force. Do we think it would be behind it? Anyway, I'm going to ask Dr. Bob that. So there is some catch-up stuff with the concepts of phase. I'll do some examples.